Welcome linear algebra fans. A video today on change of basis. So in this video we'll first talk about eigenvalues and eigenvectors of linear transformations. We'll talk about the change of basis matrix. We'll see how to represent linear transformations with matrices. And then we'll talk about how to find eigenvalues and eigenvectors of linear transformations via that change of basis or matrix representation. So here's a definition. If you have a linear transformation on the vector space V, we say that a vector little v that's an element of this vector space V is an eigenvector of this transformation T with eigenvalue lambda if the image of V under the transformation is lambda times V. So I'll briefly remind you of the similar definition for a matrix A. We say that a vector X is an eigenvector with eigenvalue lambda if AX is equal to lambda X. So sort of the same definition here. If the image of V is equal to lambda V, we say that V is an eigenvector of T with eigenvalue lambda. So here's an example of a transformation on the vector space M22. And we'll go ahead and identify eigenvectors and eigenvalues. So in this example, we're not talking about how to find these eigenvectors and eigenvalues. We're just illustrating what they are, and then we'll see how to find them a little bit later. So here is the first eigenvector, as it turns out, 0, 1, 0, 1. We'll go ahead and find the image of this vector 0, 1, 0, 1 under the transformation T. So substituting 0 for A, 1 for B, 0 for C, and 1 for D, we say that the image of A1 is 0, 2, 0, 2, which is 2 times A1. We see, therefore, that the eigenvalue associated with this eigenvector A1 is 2. So again, the image of A1 under the transformation T is lambda times A1, where lambda 1 is equal to 2. Similarly, for this A2, we see that the image of A2 is 2 times A2. So a second eigenvector associated with the eigenvalue 2 is the element 1, 1, 1, 0. Similarly, for A3, we see that T of A3 is minus 1 A3. So A3 is an eigenvector with associated eigenvalue minus 1. And the last eigenvector turns out to be negative 2. So the image under the transformation T of the element A4 is lambda 4 A4, where lambda 4 is equal to 0. Lambda 4 is equal to negative 2. Okay, we can play this game on other vector spaces as well. So here is an example on the vector space P2. Let's go ahead and have a look at this transformation R, whose image is given above. So we'll go ahead and substitute 1 for A, minus 1 for B, and 1 for C. So we see that the image of Q1 under this transformation R is 3 times Q1, so the eigenvalue associated with the eigenvector Q1 is equal to 3. Here's another eigenvector. Q2 is an eigenvector, as it turns out, x plus 2x squared. So as it turns out, the eigenvalue associated with this eigenvector is 0. We see that R of Q2 is equal to lambda 2 Q2, where lambda 2 is equal to 0. And similarly, 1 plus 4x is another eigenvalue. So the image of Q3 under the transformation R is lambda 3 Q3, with lambda 3 equal to minus 1. We notice that the kernel of this transformation R is non-trivial. Right, there is an element whose image is 0. I'll let you think about what implication this has about R, but one implication is that it cannot be invertible. Right? So So there's another implication also, and I'll let you think about that, and I'll let you work on this on the worksheet a little bit. Okay, let's go ahead and change gears a little bit and talk about the change of basis matrix. Here's the definition. The change of basis matrix on the vector space V relative to bases B and C is the matrix of the identity transformation with respect to those bases B and C. So I'll remind you that to find the matrix of the transformation T with respect to the bases B and C, we find the image of each element in B under the transformation T. We coordinatize with respect to C, and then we use the column vectors in that coordinatization process as the columns of this matrix. So the only difference here is that we're using the identity transformation instead. So really, since the identity transformation just returns us the input, we're sort of left to eliminate this step, right? So we don't have to worry about finding the image of each element in B under the transformation. All we do is coordinatize each element in B with respect to the vectors in C. Okay, so that coordinatization process gives us a bunch of column vectors, and those column vectors are the columns of the matrix of the transformation. Excuse me, those column vectors are the columns of the change of basis matrix. So a theorem here relating the coordinatization process, this theorem says that if we coordinatize any element with respect to the basis C, it's the same as coordinatizing that element with respect to the basis B and then multiplying by the change of basis matrix. So the proof of this relies on the observation that the identity transformation, when applied to the vector V, just gives you back the vector V. And in fact, this coordinatization process, rho sub C, is exactly what we do when we multiply by the change of basis matrix BC with respect to the identity transformation. Okay, so this change of basis matrix takes us from the basis B to the basis C with regard to matrix multiplication. The next theorem is a little more straightforward, intuitive. If we want to go backward from B to C, it's the same as going from C to B inverse. Okay, so I'll just let you think about that proof and read it in the book. In any case, we can go ahead and build these change of basis matrices for a change of basis matrix for these two transformations. So here we'll start off by writing the elements in B as linear combinations of the elements in C, coordinatizing the elements in B with respect to the basis C. I'm going to go ahead and call the vectors in the basis B U1 through U4 and the vectors in the basis C V1 through V4. It's pretty quick to see that U1 is equal to 1 V1 plus 0 V2 plus 0 V3 plus 0 V4. So we see that the coordinatization of U1 with respect to C is 1, 0, 0, 0. It works similarly for the other vectors in the basis B. So I'll let you go ahead and work through those details, but you should find that the coordinatization of U2 with respect to the basis C is minus 1, 1, 0, 0. The coordinatization of U3 with respect to the basis C is 0, minus 1, 1, 0. And the coordinatization of U4 with respect to the basis C is 0, 0, minus 1, 1. So we pick off those column vectors, we stick them in columns of a matrix, and that matrix is the change of basis matrix C, BC. Okay, so here's that change of basis matrix where we go ahead and exactly have the vectors that we came up with the coordinatization process as columns. So again, the coordinatization of U1 is the red column, the coordinatization of U2 is the blue column, the coordinatization of U3 is the green column, and the coordinatization of U4 is the yellow column, the fourth column. So now we can go ahead and find the coordinatization of an element, say U, just by doing matrix multiplication. Since it's quick to find the coordinatization of this element U with respect to the basis B, and since really the matrix multiplication is also pretty quick, it's pretty quick to find the coordinatization of this element U with respect to the basis C, and all it requires is matrix multiplication. Okay. Similarly, we can find the coordinatization of, we can find the change of basis matrix with respect to the bases C and B. So here we'll just do things in the reverse order and find the representation of the elements in C with respect to the basis B. The coordinatization process is pretty quick here. It's usually quick to write elements in terms of the standard basis. So we see that these are the four vectors that will become the column vectors for our matrix. Okay, so the coordinatization of V1, of V2, of V3, and of V4. So here's that change of basis matrix again. And we can similarly find rho sub B of U, and we'll go ahead and do that just by picking off the coordinates in this case. So again, writing things in terms of the standard basis is quick, but as it turns out, this rho sub B of U is equal to that change of basis matrix we just saw times whatever the coordinatization is with respect to the basis C. Okay, so let's talk about matrix representations and similarity. So here's the theorem we'll state without proof. This is kind of a complicated theorem, alphabet soup. T is a transformation with domain U and codomain V. B and C are bases of the domain. D and E are bases of the codomain. Then the matrix of the transformation T with respect to the bases B and D is equal to a change of basis matrix ED times the matrix of the transformation T with respect to the bases C and E times the change of basis matrix BC. Okay, so I won't go through the proof of this. I'll leave you to read that, but this is particularly useful when we have a transformation on the same vector space. So if T is a transformation on the same vector space V and B and C are bases, then it turns out that the matrix of the transformation T with respect to the bases B and C is similar to, right, this is a similarity transformation, the matrix of the transformation T with respect to the bases C. Okay, so it's the inverse matrix, or the transformation from C to B, that gets us there. So I'll let you read the proof of this too, but it should be pretty intuitive, right? Reading sort of from right to left, C, B comma C, takes us from basis B to basis C. Then we represent the transformation in terms of C, and then the inverse matrix takes us from C back to B again. Okay, so I won't go through this in all of its glory, but one thing we can do is think about the matrix of the transformation T from this earlier example with respect to the standard basis and with respect to this basis of eigenvectors, right? We've already identified these as eigenvectors. Again, we didn't talk about how to find those, but they are eigenvectors. So since we know the image of these different vectors under the transformation T, it turns out to be pretty quick to identify the matrices of these transformations. And I'll let you work through the details, but I'll just go ahead and write them down. So here are those matrices of matrix representations of the transformation T with respect to the basis B, a fairly simple representation, and then with respect to the basis C, a more complicated transformation. So next we can go ahead and compute the change of basis from the basis B to the basis C. And again, since the basis C is the standard basis, this turns out to be pretty straightforward. Here's that matrix where we've just identified the coordinatization of elements in the basis B with respect to elements in the basis C. Okay, and I'll leave it to you, but you should be able to find the inverse of that matrix CBC and verify that these matrices are similar. And this is a pretty cool exercise. Okay, so on to eigenvectors. It turns out that an element V is an eigenvector of the transformation T if and only if its coordinatization is an eigenvector of the matrix of the transformation with respect to the same basis. Okay, so this tells us how to find eigenvectors of a transformation. It says do a coordinatization and then find the eigenvectors of the matrix of the transformation. No big surprise there. Okay, so let's go ahead and talk about this a little bit more. Have a look at this linear transformation on M22, and we'll compute the eigenvalues and eigenvectors using two different representations. We'll start off with the standard basis, and again what we'll do here is find the image of those standard basis vectors under the transformation S and then coordinatize those, right? So we can see pretty quickly that the first column of our matrix M sub BB, the matrix of S with respect to the basis B, the standard basis, should be 0, 14, 0, negative 14, 18, and negative 6. Okay, it works similarly for the other elements in the basis, and picking those off, we can see that the matrix of the transformation S with respect to the basis B is this 4x4 matrix. The characteristic polynomial of this matrix is given as this quartic polynomial, so we can quickly pick off that the eigenvalues of the matrix are 3, 2, and a repeated eigenvalue with algebraic multiplicity 2 of -2. So let's go ahead and have a look at the eigenspaces. Of course, eigenspace is the same as the null space of M minus 3i, so we can see pretty quickly that the eigenspace of M corresponding to the eigenvalue 3 is the span of the set of vectors containing the single vector -1, 3, -3, 1. Similarly, for the eigenvalue 2, we can see that the eigenspace is the span of a set of vectors containing a single vector. Okay, and that vector is -2, 4, -3, 1. The eigenvalue with algebraic multiplicity 2 also has geometric multiplicity 2, and we can see pretty quickly that its eigenspace is the span of a set of vectors containing two vectors. And here are those two vectors of the eigenspace of the matrix M corresponding to the eigenvalue -2. One is 0, -1, 1, 0, and the other is 1, -1, 0, 1. Okay, so with those, we can pretty quickly identify the eigenvectors of the transformation with the coordinatization principle. So we decoordinatize with respect to that standard basis and come up with these four elements of M22 as the eigenvectors of our transformation. Now, if we go ahead and use the basis that is those eigenvectors, it turns out that the coordinatization, or the matrix of the transformation, is really straightforward. The coordinatization process, as it turns out, tells us that the matrix of the transformation S with respect to the basis of eigenvectors is exactly a diagonal matrix with the eigenvalues on the diagonal. Again, no big surprise there. They should be, because the eigenvectors are what does the coordinatization. Okay, so that's it, folks, for this section on eigenvalues and eigenvectors and change of basis matrix. Hope you have a lot of questions. We can talk about the worksheet more in class, and we can talk about the similarity transformation too. Have a great day, and we'll talk to you soon. So long for now. Bye-bye.